And so the first thing we did when we saw the NMOS transistor was draw its small signal equivalent, and that was and this is Gm times VGS. Now the question is, what do we do with the PMOS? All right. So remember, the PMOS, the drain current is capital ID is nothing but 1/2 in saturation is 1/2 mu P Cox W by L times VSG minus VTP the whole square. In, let us assume the transistor is operating in saturation, correct. So, what is the change in ID? So, therefore, small ID is the drain current, which is nothing but mu P Cox W by L times VSG minus VTP times the change in the source gate voltage. Okay. And this current ID is flowing, is going out of the drain, right. So, the small signal model therefore will, if you want to do it this way, will basically look like this. So, this is the source, this is the gate, this is the drain, correct. Is this clear, people? And what is the value of that controlled source? It is if you call this the incremental Gm, like we did in the NMOS case, what is that current source? VSG. All right. Okay. So, now what can you now, it is kind of a bit strange that the remember that in the incremental, in the absolute circuit, the absolute voltage of the source in the PMOS transistor will be higher than the drain, correct. But when we, for instance, when we make a common source amplifier, the source is going to be at a constant potential, right. In the NMOS case, that constant potential happened to be ground. In the PMOS case, it will be the highest potential, which will be VDD, right. So, in the incremental circuit, what happens to the source? In the incremental circuit, the source is grounded again, correct. And again we end up with this awkward situation where the ground is sitting on top and all the voltages which are in the incremental circuit are sitting below ground, right. Physically they are sitting below ground, even though they may be positive with respect to ground in the incremental circuit, right. To solve the problem, what do? You flip the whole thing again, and therefore express the incremental current in terms of VGS again, right. And what happens to the current? If I call this VGS, what should I do to that current source? What will this be? When we turn it upside down, the current was like this, and this was Gm times VSG. So, now in terms of VGS, what will it be? Well, we basically say it's we keep that, call that GM times VGS. Does it make sense, people? So, what do we conclude therefore? The incremental model for the NMOS or the PMOS transistors are identical, right? So, there's so that, I mean, once you bias the transistors up properly, whether you use an NMOS transistor or a PMOS transistor, the incremental circuit remains the same. Is that clear? Okay. Now, and of course, just like how an NMOS transistor has got finite output resistance, the PMOS transistor also has got finite output resistance, and the consequence of that we already saw. It was to simply add an output resistance RO, this is GM VGS, and similarly this is RO and this is GM VGS. Does it make sense? Okay. Now that we've seen the basic what do you call incremental equivalent circuit, I mean, we start making amplifiers like we did in the NMOS case. Let's start with the simplest one, that's basically the common source amplifier. So, what is the first bias technique that we use to generate to make the common source amplifier? Resistor divider. So, basically so with PMOS circuits often all the sources are connected to the topmost rail, right, and if you call that VDD, and now what is the source gate voltage? What is the source gate voltage? VDD times R1 by R1 plus R2, okay, and so as long as that is greater than VT, you will have some current flowing, and therefore you will have some transconductance, correct. Now, what comment can you make about now if you want to make a common source amplifier, what all should we do? So, again same old, that is the input voltage, okay. What about the load now? You can put it in the drain directly. If you are concerned about DC current flowing through the load, then you can, as usual, couple it to the capacitor, okay. And so the so Vg is VDD times R2 by R1 plus R2. So, Vsg is nothing but VDD times R1 over R1 plus R2. Id therefore is nothing but 1/2 mu p Cox W by L times Vsg minus Vtp the whole square. So, the drain potential, the quiescent drain voltage is the quiescent voltage of the drain is nothing but Id times RL, okay. and okay. Now, if you want to make the incremental equivalent, how does the incremental equivalent look? The capacitor becomes a short, that is Vi. Then you have R1 parallel R2 and what is the equivalent? This is Gm times Vi, which is happens to be Vgs in this case, and then it is RL and the output is Vo. And what is the incremental gain? Minus Gm RL, right. This is the same old common source amplifier that we have looked at. Is it clear? Okay. Alright, so now let us take a look at the, let us say I had an NMOS transistor and a PMOS device, and let us say for argument's sake that mu n Cox W by L for the NMOS transistor is the same as mu p Cox W by L. Let us also say that VTP is the same as VTN. Okay. Now, I want to just point out something. So, let us say we have an NMOS circuit, something like this. Okay, this is just an example. Say R1, R2, RL. This is some VDD. Okay. So, what is the gate source voltage? VDD times R2 by R1 plus R2. Great. Now, if I want to replace, and there is some drain current here, which is whatever, right, Vg minus Vt and the whole square times half mu n Cox W by L. Now, let us say I wanted to replace this transistor, if I wanted to realize the same common source amplifier with a PMOS device, right. If I wanted to replace the transistor with a PMOS device, alright, what comment can I make about, first job of course is to bias the transistor. So, earlier VGS has to be, in the NMOS case VGS has to be positive, right, gate has to be higher than the source. So, in the PMOS case VGS must be negative, right. So, if you did not want to change anything as far as the topology is concerned, what would you do? You just replace this VDD with minus VDD. Correct? All right. Okay. So, consequently what will happen? All the VGS, the quiescent values, what have you done? I mean, remember that in this case what you have is a transistor. Around the transistor you have some network with resistors, correct? Okay, this is some resistive network, correct? This is what we use for biasing, correct? And there is a battery VDD. and the operating point is established by this combination of this battery and this resistive network, correct. Okay. Now, if you want to replace this NMOS transistor with a PMOS one, and assuming that the PMOS transistor has the same threshold and the same mu n Cox W by L and mu p Cox W by L, what should we do to all the to the quiescent voltages at these nodes? We need to reverse them. So what is what is the easiest? I mean, how do you think we can reverse them? All that we need to do in the PMOS case is to simply take whatever NMOS network we have, we flip the direction of the VDD, then what can you do? You just simply remove the NMOS and put a PMOS, right. Earlier the gate was higher than the source, now the source is higher than the gate, but the gate source voltage will remain exactly the same, and likewise the direction of the current will be opposite, but the magnitude of the current will be exactly the same. Does that make sense? And as an example, you can see here, so the source gate voltage, in this case the gate source voltage was VDD times R2 by R1 plus R2. Now the source gate voltage is VDD times R2 by R1 plus R2. So earlier the current ID was flowing downwards, now the current is flowing, the same current ID is flowing upwards. Alright, but of course we don't like negative voltages first, right. So if we don't like negative voltages, what do? All the voltages, I mean, the highest potential is 0 and the lowest potential is negative VDD, which we don't like. So what do? Add VDD to all nodes. So basically then this node becomes ground. What does the lowest node become? That is VDD. So nothing changes, correct. Okay. All right. Now, what is something else that we don't like? The higher potential is below and the lower potential is above. So we don't like that. So we, you just redraw the circuit so that VDD is on top. That is RL, this is VDD. Yeah, what must be the upper resistor in the bias network? R2, and this is R1. So, this guy and this guy will have exactly the same operating point, same incremental gain, same everything, provided the transistors are identical except for the NMOS being PMOS. And okay, that means that the moment you see a circuit with NMOS transistors, right, you can convert it into a circuit with PMOS transistors by simply first thing to do is replace every NMOS transistor with a PMOS transistor, replace all positive batteries with negative batteries. Then you don't like negative voltages, so you add appropriate voltage so that the lowest potential becomes 0 and not negative. And then since the directions of the currents are all going upside down, you turn the circuit upside down, and therefore then you will get a PMOS circuit which operates between positive supply and ground, and where current flows from a current of course always flows from a positive potential to a lower potential, but in the page it will flow from upwards to downwards, right. So, so by attending this class, you basically doubled the number of circuits you know, right, because every circuit you knew before can be converted into something with PMOS, right. The only thing is it takes a little while getting used to, because everything is kind of reversed, right, but after a little bit of practice you will find that working with PMOS transistors is just as easy or difficult as working with NMOS transistors, right. And as he pointed out, it turns out that I think you probably know this already from your device classes, but as you know, the mobility of holes at least in older technologies was smaller than the mobility of electrons, and therefore PMOS transistor, that mu p turns out to be smaller, maybe by a factor of 2, 3, something like that, right. And therefore inherently, if you want to have the same transconductance with a PMOS device, you must increase the size of the device, okay. And so indeed it turns out that PMOS transistors are slower than NMOS transistors. However, we still need them and use them because of their complementary property. Does it make sense? Okay.